Swayam Prabha. Digital India. Educated India.
In this part, we'll look at a couple of degenerate cases, which are still concepts which are useful in circuit design. Okay, and these are open and short circuits. Now, when I say a short circuit, I have to say that it's a short circuit between these two nodes N1 and N2. Okay, there are many ways to consider this. So let's say I have a node N1 here and I have a node N2 here, and I say that there is a short circuit between them. We know that a short circuit is nothing but an ideal wire connecting these two. So there are many ways to deal with this. So firstly, one thing we can do is not treat these as two separate nodes, but treat them as a single node. Okay. Okay. Now that's always possible. We don't even consider two separate nodes, but many times, maybe while in the course of analysis we would have considered two separate nodes and there happens to be a short circuit between them. All these are possible. So we'll look at the nature of this short circuit. It's quite trivial really, but we'll still look at that. Okay. So what does a short circuit between N1 and N2 mean? It means that there is zero voltage difference between the two nodes. Okay. Now, zero voltage between these two nodes. Okay. So if I go and draw the IV characteristic of this, obviously the voltage is always zero and any current can flow through the short circuit or this wire. So the characteristic looks like this. It's a vertical line passing through the origin. Okay. Now from this it's obvious that this can be represented as a voltage source of value 0, which is also equivalent to a resistance source, a resistance of value 0. Okay. So these, obviously you know that if R is 0, then from V equals IR, V will always be equal to 0. Okay. So these are all equivalent concepts to having a short circuit between these two nodes. That's why I brought up this thing in the first place. Okay. Now similarly, you can also think of this as zero inductance between two nodes. Okay. Because we know that V is L times the time derivative of I. This means that for any finite value of the time derivative, the voltage will still be 0. Okay. And finally, I won't go and prove this, but you can reason it out for yourselves that this is also equivalent to having a capacitance which is infinity. Okay. So if a capacitance is infinity, then the two nodes across which the capacitance is connected will be constrained to have the same value. That is, the two nodes will be at the same voltage. Okay. So a similar concept is an open circuit. So open circuit really means that there is no connection between these two nodes. An open circuit means no current flows between these two nodes. In other words, current equals 0. Okay. So what does this mean? You can equivalently represent it with a zero current source. Okay, because if current is 0 and I draw the IV characteristic of it, I'll have a horizontal line passing through the origin that corresponds to I equals 0. So that is a zero valued current source, which is also equivalent to an infinite valued resistance or zero valued conductance. And again, I won't prove this, but you can very easily reason it out for yourselves that this is equivalent to a zero valued capacitance or an infinitely large inductance. Okay, so that's an open circuit. So sometimes it's useful to think of either an open circuit or a short circuit as these elements with these extreme values. Okay.